Good afternoon to everyone. I welcome all of you to the 81st lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Dr. Umeshkanta Singh from Bennett University, Noida. Dr. Umeshkanta Singh obtained his PhD from Jawaharlal Nehru University, New Delhi in the year 2011. He carried out his postdoctoral studies about 2 years. The first one at Max Planck Institute for the Mathematics in Sciences, Leipzig, Germany, and the second one at Louisiana State University, New Orleans, USA. He then came back to India and joined as an assistant professor at Central University of Rajasthan in the year 2014, and then moved to Ashoka University in the year 2016. He joined Bennett University in the year 2020, and right now he is serving as an associate professor. Dr. Umeshkanta Singh research interests cover nonlinear dynamics of coupled oscillators, synchronization of complex networks, and stochastic chemical kinetics. He has made notable contributions to these areas of research. I met Dr. Umeshkanta Singh in an annual meeting held at Delhi a few months ago. In fact, Dr. Singh was the organizer of the meeting, and several young people working in nonlinear dynamics presented their work in the meeting. When I inquired him about the possibility to deliver a lecture in this forum, Dr. Singh immediately gave his consent. Thank you, sir, for accepting our invitation and delivering a lecture in this forum. With this short introduction, now I invite Dr. Umeshkanta Singh to deliver his lecture. Over to you, Professor.
So thank you very much, Professor Senthil Veland, for giving me a chance to share my work to a larger audience in nonlinear science community. So I will share my screen and I will start my presentation. So I hope my screen is visible.
Yes,
okay.
yes.
Yeah, so thank you very much for giving me a chance to speak about my work in a larger community who are working in nonlinear science. So today I'm going to talk about some work that I have done by using the coupled oscillators. And I put the title as like some adventures in the world of coupled oscillators. And here is the brief outline of my talk. So first, I will give a small motivation why I am studying this coupled oscillators. And the motivation is the phenomena of synchronization that we have in our so I will discuss about the Stuart-Landau oscillators and the reduction to the Kuramoto oscillators. And after that, I will discuss about my work, which is about the linear stability conditions for synchrony in time delay coupled systems on star network, where we have heterogeneity in the connections. And so using these stability conditions for synchrony, so I will show you the functional equivalence of two different network topology. One is the Cayley tree and the star network. And after that, I will discuss about the continuous and discontinuous transitions to synchrony by considering a network of time delay coupled phase oscillators on star network. And finally, I will briefly discuss about the current work which I am doing with my students at Bennett, which is the heterogeneity-induced synchrony. And after that, I will conclude by giving a summary. So we all know that synchronization is a phenomena which can be found in our life. Like, so one example we can cite from biology is the synchronizations of the cardiac cell, which give rise to heartbeats. And so on the other hand, there are situations where synchrony is not desirable in our life. Like, for example, when we have synchronization of the pedestrian's footsteps on a swinging bridge, then there are so there is a possibility that there are resonance motion developing in the system, and that can lead to the destruction of the breeze. So, so we have one situation where synchrony is useful, and we have some situations where synchrony is not desirable. So, for example, for the case of this synchrony of cardiac cells, the heartbeat gives rise to the blood circulation, and on the other hand, the synchrony of the pedestrian footsteps on a swimming breeze can give rise to the phenomenon of resonance, which can lead to the destruction of the breeze. So it's important to understand how synchrony develops in the group of system. And so here I'm showing an example of a population of fireflies which are passing in synchrony like during and such kind of systems where you have synchrony, we can study like by considering the mathematical framework of coupled differential equations. And in my work, I use a system of coupled differential equations, ordinary differential equations, and I also put some time delay in the coupling, which can incorporate the finite speed of signal transmission from one unit to the neighbors. And we can also consider only the phase dynamics of the coupled oscillators, and that transition we can do by considering a weak coupling situation. And I'm going to discuss what we mean by weak coupling. So by considering the reduction of the Kuramoto phase oscillator from a system of Stuart-Landau oscillator. And here we can see that, so when we talk about coupled oscillators, we have a frequency of the units. We can have the network topology of the systems where different units, they communicate to each other. And we have a nonlinear functions, which is basically the coupling function for the system. And we can see that we can have a different network topology. Here I am showing an example of a star network. And the second example I am citing from biology, which is the symbiotically connected species. And this is a bipartite network where you have two partitions, and the units of one partition, they communicate with the units of the second partition. And the third example, I'm taking a small example of a neural network, which can be represented by a Cayley tree. So, so here I want to briefly discuss how we can consider a biological oscillator. Say, for example, a passing firefly with the rotational motion. So a particle which is traveling on a circle with speed omega, and we know that for this particular situations when you have a rotational motion on a unit circle, so you have a very simple equation, and so this simple equation, so d theta by dt, which is the rate of change of angular displacement, gives you the frequency of that particle, which is so which is traveling on this circle. And using a complex notation, you can also write down. So you can also write down the set of equation, by using a complex variable where you have z, which is equals to r e to the power I theta. And so here is the situation where you can model the rhythms of a firefly, by using the phase oscillator. And we know that the phase of an oscillator, they can take values from 0 to 2 pi, and here the phase is growing linearly with time. And we know that firefly, so they emit light pulses so regularly, and here I'm making a representation that at every time period t, so this firefly is emitting some light pulse. And so here we can see that by considering a simple example of a particle which is moving with a uniform speed, we can model the dynamics of a firefly using that simple set of equations. And so this Stuart-Landau oscillator is a nonlinear prototype to understand how oscillations that develop in nonlinear systems. And here you can see that in this differential equation, we have a nonlinear term, and due to the presence of this nonlinear term, so there is a possibility that we have a closed solution in the phase space, which is called the limit cycle. And the motion of this system we can understand properly by transforming to a set of polar form, where dr by dt tells you how the amplitude of the system, so they varies with time. And then we have another equation which tells about the phase variation of the system. And here you have a two differential equation which is totally decoupled. And from this, we can understand how the formation of the limit cycle can be developed when you sense the control parameter A in the system. So here we have two set of equations, one which describes the variation of the amplitude, and the second equation which describes the variation of the phase, and that second equation gives you the phase equation. And so we can consider a population of these Stuart-Landau oscillators with the mean field coupling. And here in this set of equations, so this last term with the summation is the mean field coupling, and we can understand the mean field coupling physically by considering a situation that the oscillators, they feel the effect of the whole population. And for this couple Stuart-Landau oscillators, we can also get two equations. One is describe the radial, and the second equation which describes the phase of the oscillations for each Stuart-Landau oscillator. And so when we consider the situation that oscillators, they go to this, so go to the limit cycle very quickly, then in that situation, we can consider that there is no variation of the amplitude. So we can completely ignore the first equation, and we just have a single differential equation for the phase. And using this simple equation, one can understand how this frequency, which is given by omega k, changes when we have the coupling in the system. And here you can see that we have the coupling in the form of the sum of the sinusoidal function, and we know that sine function can give two values, okay, one positive and one negative. And so from this coupling function, okay, you can see that the sign of the net sum of this coupling function, okay, can be positive. Okay, when we have that situation, so the oscillators speeds up, and on the other hand, we have a second possibility where the sign of the net sum of the coupling is negative, and in that situation, oscillator slows down. So here in this, we have a nonlinear coupling, which is given by the sinusoidal function, and the role of the sinusoidal function is to speed up or slow down this phase oscillator when you change the coupling strength gradually in the system. And this Kuramoto model is one of the simple and powerful tools to understand how synchronization can develop in various complex systems. And so we know that complex systems can have various things like you can have very complicated network topology. So this network topology is given by this adjacency matrix AIJ, and this model, so this Kuramoto model is flexible enough to introduce the time delay in the coupling. So here tau is the time delay, and we can also add a phase translation parameter alpha, which can prevent the phase oscillators to go to a regime of complete synchrony. And we can also add noise to the system to understand how noise affects the collective motion of the phase oscillators, or how noise can affect the dynamics to go to some regime of order or some regime of disorder. And you can see that this Kuramoto model can be used to understand various diverse systems. Like, for example, this model can be used to understand the mechanical oscillators, electronic oscillators, and a network of biological oscillators. And this, and here I'm citing a review paper in the Review of Modern Physics. So now the next question is how do we quantify synchrony in a group of a couple oscillators, in particular the phase oscillators? And there can be two situations where we have a continuous transition from a regime where there is no synchrony to a regime where we have synchrony. So when you change for the first case, I'm showing a schematic diagram of the situations where we have a smooth transition from a regime where there is no synchrony to a regime where we have synchrony gradually when you increase the coupling strength. And one example we can cite is this flashing FIREFLY, where fireflies, okay, they try to try to go towards the collective behavior by changing their rhythms gradually in tune with the dynamics of the population. And on the other hand, we can have a transition which is not continuous. Say, for example, for the case of synchrony in suspension breeze, so there is a sudden transition from a step where you don't have a synchrony to a regime where you have a synchrony. And this kind of situations where you have a discontinuous transition, so we have this explosive synchronization in the system. And this quantification of synchrony we can understand by considering the idea of vectors, where we can have a resultant vectors, and these so here in this set of mathematical equations where we have the other parameter in the system, so this R, capital R, is basically the magnitude of the resultant vector divided by the total number of the oscillators in the system. And you can see that this capital R, which is the other parameter which can quantify the degree of synchronization, can take values from 0 to 1. So when you have this other parameter 0, the system is in a desynchronization state. And when you have this other parameter value, which is equals to 1, you have a fully synchronized state. So the question is how, what are the possible transitions? So we can have two types of transitions where you have a continuous growth from 0 to 1. And the second possibility is that we have a sudden jump from a from a regime where the order parameter is 0 to a finite value. And this set of equation basically, so they bridge the microscopic quantities to the macroscopic quantities that we use to quantify the degree of synchronization. And so with this background, I'm going to discuss the dynamics of time delay phase oscillators. And so before I go to my work, I want to give some background about some studies where time delay is considered in the coupling. So here we have two phase oscillators, which is coupled with time delay. And one can work out to find out the common frequency of these two phase oscillators, which is coupled with the time delay. And the expression so we can get is this given by this formula. And here we can see that this is a transcendental equation. And so this transcendental equation says that there is a possibility that we can have multiple stable solutions in the system, and that multiple stable solutions are possible because these time delay coupled systems have infinite dimension. So because of this infinite dimension, so there is a possibility that we have a multitude of synchronized solutions when we incorporate time delay in the system. And the second possibility is that since we have the second possibility is that there is a possibility to change state from in-phase synchronized state to a anti-phase synchronized state. And further, Earl and Strogras, they came up with a stability condition for synchrony of identical oscillators for arbitrary network, and they made some approximations, and two things that we should note. The first thing is that they have considered the identical frequency. So here in this set of equation, so all the oscillators have the same frequency. And the second thing is that the coupling is normalized by the degree, okay, the number of connections and not have. And these two conditions give rise to a situation that all the oscillators, they have same input, okay, from the neighbors. And for this, we can have a transcendental equation, a single transcendental equation, which can describe the in-phase synchrony frequency. And there is a single condition which can give the linear stability condition, and that linear stability condition is given by the derivative of the modulating function that you have in the transcendental equation of the common frequency. So the next question is what happens when we have degree heterogeneity in the system? So this was the first question that I asked. So this is my first work in this time delay coupled system. And so before proceeding to my work, I want to just tell you some of the features of the real network. So some features of the real network is that they have this scale-free property, and they have hubs which are highly connected. And you can see from this picture that this hub has many connections compared to the peripheral the peripheral units. And we can consider two types of heterogeneity for simplicity. So one is the degree heterogeneity, and the second is the frequency heterogeneity for the system. So I consider identical phase oscillator with the degree heterogeneity. So here, this half has n-1 connection, and this peripheral oscillator has only one connection. And to get the expression for the collective frequency, which is given by capital omega, we need to consider like two answers separately, one for the peripheral oscillators and one for the hub, where you have a phase shift in this phase term, which is given by capital omega t. And we can understand the development of this phase, okay, by considering a simple example from physics, where we have three coupled mass. So for these simple systems where you have three coupled mass, we have three modes of oscillation. The first mode of oscillation is that all the oscillators, so they are in the same phase. And here you can see that the first mode of oscillation, the middle oscillator is leading the phase, and the peripheral oscillators, okay, they have a small phase lag up here to the middle oscillator. And the second possibility is that the two peripheral oscillators are like the anti-phase, while the middle oscillator has no motion. And the third possibility is that the two outer oscillators, they are in phase, and so these peripheral oscillators are anti-phase, okay, with respect to the middle oscillator. And so motivated by this, we have also studied the dynamics of three Stuart-Landau oscillators with time delay coupling. And here we can also see the similar dynamical behavior that we can observe for three coupled mass. So here we have three separate regimes. So one, this frequency, so this lower branch, which is the frequency of the in-phase synchronization. And then you have a regime where the two outer oscillators are like anti-phase. And then we have a higher frequency branch where the two outer oscillators, so they are in phase, and all right. So for the case of star network with this degree heterogeneity, we can obtain the expression for the common frequency and the phase shift between the oscillators. So this is the phase shift between the peripheral and the hub oscillator. So one can find out this mathematical equation, and we can also study how this frequency depends on the network size, which is given by capital N. And we can also find out the expression in the thermodynamic limit, where N goes to infinity, and these are the two equations for the collective frequency and the phase of the hub and the peripheral oscillators. And for this, we get, so for this, so we derive the linear stability criteria for synchronization. And here we have two conditions for the in-phase synchrony, and we can also have two conditions for the out-of-phase synchrony between the peripheral and hub oscillators. So here we can see that when we have a degree heterogeneity, the linear stability conditions, they changes, and because of these, okay, we have two stability conditions which needs to be satisfied simultaneously to have the in-phase or out of phase synchronization. So here is the comparison between the analytical and the numerical simulation results. So, so this dotted, so these points which are represented by blue, so these are the stability, linearly stable solutions, and this curve are the numerical solutions. And here you can see that for the synchronized regime, there is a good agreement between the analytical estimates and the numerical estimates for the system. And this is the phase diagram of the system in the parameter space of the coupling and the time delay. So the next question that I ask is, can we understand a slightly complicated network structure by using the linear stability conditions that we derive for the star network? So here we have a Cayley tree, and this Cayley tree, so we can consider in terms of different cluster. Okay, so you have the central node, which is represented by C1. You have the first layer, which is represented by C1, second layer C2, third layer C3, fourth layer is C4. And when we consider these identical oscillators, we can vary the time delay and understand, okay, what kind of dynamics can arise in this system. And here we can see that we have, so we have a regime where we have a clustered synchrony. So the oscillators in different layers, they group together, and all these clusters, they have a collective single frequency in the system. And when you change the time delay, you have a region of desynchrony. And when you change the delay further, so there is a phase flip transition between the cluster. And from the time series, okay, we can see that change in the dynamics when you vary the time delay in the system. So here is the comparison between the synchronous solution, which we obtain numerically for the Cayley tree, and that is represented by these dotted curves. And these points, red, green, and blue, are the points which we obtain by using the linear stability conditions that we derive for the case of the star network by considering the degree heterogeneity. And here we can see that there is a good agreement between the dynamics that we obtain for the Cayley tree with the linear stability conditions that we obtain for the case of star network. So one reason is that these two networks, so they look different, but they belong to a same class, okay, which is the bipartite network. And because of that, so here we can consider that in the synchronized regime, the nodes which are lying in the core of the Cayley tree can be converged to a single cluster. And when we have that situation, this Cayley tree can be so this Cayley tree can be reduced to a star network with a central node and the peripheral oscillators. So next, we study how the time delay, so they affect this transition from a regime where we don't have a synchrony to a regime where we have a synchrony. So how delay affects these transitional goods to synchronized regime, and for that we consider a system where we have a degree frequency correlated system. So that means that the frequency of the frequency of the units that we are considering. So that depends on the number of connections they have. So for example here, so this hub frequency, which is represented by omega s, is given by n minus 1 omega p. So here the frequency of the oscillators, they depends on the number of connections have. And for this case, we can identify two frequencies. Okay, one is the average frequency of the units that we have in the system, and the other frequency is the frequency detuning, which is the difference of the frequency of the half and the peripheral oscillators divided by the total number of oscillators that we have in the system. And for this, we have two finite quantities. One is the average frequency. So this gives rise to a time scale. Okay, so here this time scale is represented by EAV. And from this frequency detuning, we can get the condition for the threshold coupling for the onset of global synchronization in the system. So here is the summary of the result that we have. And so we can see that from this schematic diagram, for time delay, which is lying between this, so this half of the average time period, so they give rise to continuous transition to synchrony, and that I'm showing here for the left panel here. Okay, so here I'm showing the other parameter variation with the coupling strength, and you can see that you have a smooth transition when you consider the values of the time delay in the range which is given by half of the average time period of the system. So on the other hand, if you consider the value of the time delay in this range where you have this average time period TAV divided by 2, and you have this average time period T. So when the value of the time delay is taken from this range, you have a explosive synchronization in the system, and that we can see from the variation of the shorter parameter as a function of coupling strength. So the idea is that, so here in this figure, on the right hand side, I am showing the variation of the common frequency of the system with time delay, and you can see that we have a series of saddle node bifurcations at different points. And here you can see that the average time period is given by this red arrow. Suppose if I consider a time delay value lying between this region, so there is a continuous transition. And if you change the time delay and consider a value in this range, then we have a explosive transition. And since the system has some kind of a periodic behavior, so similar behavior, so there is a similar dynamics of when you go to this time interval or when you go to this time interval. So here, when you take a value of delay parameter in this regime, you can have a continuous transition to synchrony. And on the other hand, if you consider a value of time delay in this interval, you will get the transition to synchrony, which is not continuous. So here, there is a interplay between the time delay and the average time period, which is induced by the average of the intrinsic frequency that you are considering in the system. So these are some of the mechanisms that people have proposed for the development of the explosive synchronization in complex network. And here I am showing two mechanisms. So one is this degree structure dynamics correlation, which I have used in my work. And the other mechanism is the frequency coupling correlation, that the frequency, so the coupling terms, so they also have this frequency. So these two conditions, they avoids the flexibility and generality and applicability. And the next question is like, is there a possibility to have explosive synchronization with just frequency heterogeneity in the system? And for that, we consider a simple star network. So here we are not considering any time delay in the system. We just consider frequency heterogeneity. So one frequency for the peripheral oscillator and one frequency for the hub oscillator. And for this simple system, we can get the microscopic dynamics, okay, the time evolution of the order parameter and the time evolution of the phase. The exact mathematical equation, okay, for the time evolution of the microscopic dynamics. And from this, we can get an expression which can describe the coherence or the decoherence state which is present in the system. And here, in this work, what we have shown is that just by the presence of frequency heterogeneity, we can have explosive synchronization in the system. And further, we also consider a full bipartite network where we consider two layers with 100 oscillator each. And for this case also, we can get the exact analytical expression which governs the synchronization state. And here you can see that there is a good agreement with the analytical estimates and the numerical estimates for the synchronization state. And okay. And finally, I want to discuss some work that I have been doing with my student at Benet University. So here we are trying to understand the phenomena of this heterogeneity-induced synchronization. And for that, we consider a time delay coupled Stuart-Landau oscillator. And so this is the work that we are trying to follow, like we are trying to generate the result, okay, which is given in this particular work, and we have been successful to generate the results, and at the same time, we are able to take the work further. So here we have a systems of Stuart-Landau oscillator with time delay coupling, and here the amplitude of these Stuart-Landau oscillators. So here the frequency of these Stuart-Landau oscillators, they depend on the amplitude. So the frequency of the oscillators, okay, you can find out from this set of equation is given by omega k. So this is the base frequency, and we have a term which depends on the amplitude of the oscillator. So this is a situation where we have amplitude dependent frequency, and we can have two cases where we have a homogeneous frequency. So for that case, this omega k has the same value, and that we can see by considering a delta function. And for the heterogeneous case, okay, we can consider a distribution and in the work, so that is reported in this Penna's paper, so they have considered a Gaussian distribution for the case of heterogeneous frequency. So here is the phase diagram for the homogeneous case and the heterogeneous case. So the phase diagram is plotted in the parameter space of the coupling and this time delay tau. So here, these white regions, they represent the synchronous regime, which we find out by considering the frequency deviation from the which we found out from the frequency deviation of the average frequency. And this black region, so they represents the region where we have the synchrony. So when we when some heterogeneity is incorporated in the system, the structure of the phase diagram completely changes. So this big region, which is the synchron, which is the region of the synchrony, so they vanish away from this phase space, and at the same time, the small region which is present here, okay, they begins to grow. So this is the situation where you have a synchrony in the parameter regime where identical oscillators cannot synchronize. So I'm going to consider this line, which is represented by k equals to 0.3. So this is the coupling value that we are going to consider, and we will vary time delay to understand, okay, how the frequency of the oscillators and the other parameters, okay, they vary as a function of time delay. So this is the situation for the homogeneous oscillator. So this is a system of coupled Stuart-Landau oscillators on the ring. Here we can see that there is a transition from a regime where you have a single frequency branch. So this is the region where we have this synchronization of the identical oscillators, and there is a point where there is a onset of the desynchronous regime. Okay, so this is the variation of the collective frequency of the system with time delay, and here we are showing the time series of the oscillator in the synchronous regime and in the desynchrony regime. So you can see that by changing the time delay, so there is a transition from the synchronous regime to the desynchrony regime. So the next question is, what happens if we change this frequency, this base frequency, by introducing some slight heterogeneity in the system? So this is the so on the left side is the variation of the collective frequency. So there is a, so when the time delay is small, the system is not synchronized. When delay is slightly increased further, there is a regime of synchronization in the system. And on the right hand side, the time series of the oscillator in the desynchrony and the synchronous regime is shown here. So this gives the idea of heterogeneity-induced synchronization. So the idea is that when we have some heterogeneity in the system is able to synchronize in the parameter regime where identical oscillators cannot synchronize. And that we can see from the phase space of the two cases, first for the homogeneous case and second for the heterogeneous case. So right now we are trying to, so we are working to find out the stability of the synchronous solutions by changing these Stuart-Landau oscillators to a coupled Kuramoto oscillators. Okay, so here is the summary of my talk. So the first point is that so to understand the synchronization phenomena that we have in our day-to-day life, so these coupled oscillators, particularly the Kuramoto phase oscillator. So this is a very powerful, which is simple enough to do the analytical workout to understand how synchronization arises in complex systems. And we have derived the linear stability condition for a heterogeneous network. So by considering a specific network, which is the star network, and this star network we considered with two different types of connection, and so that so that mathematical condition which governs the synchronization of phase oscillator on star network, they are able to describe the linearly stable solutions that we have for the Cayley tree, and this gives us the idea about the functional equivalence of two different networks. And so right now, so we are working to find out the possibility of generalization for a class of bipartite network. And in the fourth point, we have studied the interplay of the time period which is induced by average of the intrinsic frequencies and time delay to understand the time delay intervals where we have a continuous transition to synchrony and discontinuous transitions to synchrony. And then we also studied a situations where a frequency mismatch can give rise to explosive synchrony. And for these bipartite networks, exact analytical estimate of the order parameter is possible, which is in complete agreement with the simulation results for the system. And finally, for the case of coupled Stuart-Landau oscillators on a ring, so heterogeneity, presence of heterogeneity can give rise to synchrony in the parameter regime where homogeneous oscillators can't synchronize. Yeah, thank you very much.
Thank you, Professor. Thank you.
Yeah.
So the forum is open for clarifications, questions, doubts. Students, you may raise your questions by unmuting, or you can put your question in the chat box.
Hello, sir.
Yes.
In bipartite network.
Yeah, please.
Both group contains n number of oscillators, or group A contains n number of oscillators and group B contains n number of oscillators.
Yes.
So, not overall n number of oscillators.
Can you repeat the question again?
Sir, in bipartite network, oscillators are split into two groups.
Yes.
A group contains n number of oscillator or n by 2 number of oscillators.
So this star network
Yes.
is also a bipartite network. Okay, so we can group the nodes. So like one for the hub and one for the peripherals. So for this particular case, the number of the number of units in the partitions are not same.
Okay.
So we can have a fully bipartite case, okay, where you have two partitions with the same number of the oscillators, okay, in the two different partitions.
Okay. Okay.
So this Cayley tree star network, okay, they belongs to this bipartite network.
Okay. Sir.
Kamalasan, do you have any other question?
Sir, nothing, sir.
Students, you may raise your questions now.
Sir,
Yes.
I have another one question.
Yeah, go ahead.
Sir, in star network,
Yes.
only one oscillators are coupled to all other oscillators.
Right.
Remaining oscillators are only one interactions between the other oscillators.
Yes.
Sir, in star-like network, one oscillators are coupled to all other
Yes. The hub. Yeah. The hub is coupled to the peripheral.
between, and another oscillators only coupled to the hub.
Yes.
There is no link between other remaining oscillators.
No, the peripheral oscillators are coupled with each other, or
The peripheral oscillators are not coupled to each other.
Not coupled.
So the peripheral oscillators are only coupled to the hub.
Okay, sir.
they are not coupled with each other.
Yes, they are not coupled to each other.
That time AIJ score is 0. Sir, AIJ, oscillator index, AIJs are 0. In equation, you have mentioned summation over J is equal to I minus 1 to N minus 1. I is equal to 1 to N minus 1.
Yeah.
So that coupling functions from one oscillator are coupled to all other for equation.
Yes. Let me go back. Yeah. Let me go to
Yes.
the set of equation.
And phi n dot equal to omega plus epsilon I is equal to 1 to n minus 1. It's coupled to all other oscillators.
Yes, the hub is coupled to the
All
peripheral. Yeah.
In n plus or n minus 1 oscillator.
So, like, suppose if you are considering a star network of n oscillators, so this hub, okay, this hub has to be coupled with n minus 1 oscillator.
Okay, sir.
Students, yeah, we are not getting any questions from the students.
No problem.
Maybe they will write to you. They are
Yes. So since this is a Friday evening, yeah.
Since there are no more questions, I would like to conclude the session.
Yeah, thank you very much, Professor.
I would like to conclude the session by thanking Professor Umeshkanta Singh for accepting our invitation and giving a very elementary on the current scenario in coupled oscillators. Thank you, sir. Thank you very much.
Yeah, thank you very much, Professor Santilvelan, for the opportunity to share my work.
Nice to see you again.
Yeah, hope to see you soon. Thank you very much.
Thanks, sir.